Hello, my dear friends. Today I'm full of energy and enthusiasm to show you a solution of a very, I would say, complex physical chemistry problem. It's related to the use and application of statistical thermodynamics in chemistry. Well, in particular, we're going to investigate the properties of molecules because this is what chemists are mainly interested in: the behavior of molecules characteristics, and their calculations. Okay, and why am I saying that it is a complex problem? Because in this problem, we are expected to find numerical values of a number of typical physical chemistry characteristics of a molecule, such as entropy, internal energy, enthalpy, etc. Okay, let's get down to the problem right now, and the problem itself is going to show up on the screen of your computers right now. Here it is. Hope that you can see it. So we have been given the molecule of carbon dioxide, and the temperature is 298 kelvins, and the pressure is standard 1 atmosphere, and they want us to calculate internal energy, U minus U sub 0, enthalpy, H minus H sub 0. Many people still don't know these symbols, why we got two seemingly alike symbols, 0 up and 0 down. Actually, the upper symbol means that we are dealing with a system which is under the pressure which is equal to 1 atmosphere, standard pressure, okay? And the lower 0 stands for the temperature, which is equal to 0 kelvins, okay? For that reason, this notation means that we are going to calculate isobaric heat capacity at the standard pressure of which is equal to 1 atmosphere. The same is about this notation as 0 sub t. That means that we are wanted to calculate the value of the entropy at temperature, given temperature T, but at 1 atmosphere. And also they want us to calculate reduced Helmholtz energy and reduced Gibbs energy. Okay, so let's do it. I hope that on the basis of your working experience, your calculation skills related to physical chemistry can do it, as they say, hands down. Well, and you can pause the video in order to do it on your own, and then you can compare your answers with mine. And if your answers are far from mine, so it means that you may have made a mistake, and for that reason, you'd better watch the video again in order to put yourself on the right track. Well, let's start from the first moment. It is the internal energy calculation. We remember that absolutely all thermodynamic parameters, including internal energy, can be expressed as the sum of these parameters, their components related to translational motion, okay, rotary motion, vibration motion, and electronic, right? Electronic component is also taken into consideration. Okay, now let's do it. So we can write that U minus U sub 0 is equal to U minus U sub 0 translational plus U minus U sub 0 rotary, okay, plus U minus U sub 0 vibration, right? Okay, and now we're going to calculate each of these three components one by one. So the first one, you should remember from the course of general physics and chemistry, actually, that the degree of freedom of translation motion, okay, is equal to 3. because a particle moves in three dimension, and for that reason it has got 3 degrees of freedom. And for that reason, this component is equal to I sub Tr times the gas constant R halved. Yes, and that means that we can calculate it right now. Remember the value of the gas constant, and it gives us the value of the translational component of the inner internal energy. It's 3,718.23 joules per mole. Okay, so we've done it with it. Okay, now we are proceeding to this one, the second component, which is related to rotation. So U minus U sub 0 rotary, okay, is equal to, the formula is nearly the same, but the subscript will be different because this time we are dealing with the rotation. For that reason, we are dealing with the rotation movement degree of freedom times R halved. And we should remember from the course of chemistry, general chemistry, that the geometry of this molecule is linear. It is a typical linear molecule, and it will play its role in a few moments. But right now, it's still important to take this fact into consideration. And that means that for a linear molecule, this degree of freedom in rotation motion is equal to 2. This cancels, and we've got 8.314 joules per mole. Okay, so far so good. And now we're proceeding to the third component, which is U minus U sub 0 vibration. Sometimes I say oscillation. I hope that it's comprehensible. Okay. And in this case, we've got a big question, because many people don't know how to do that. Firstly, we need to turn to a good reference book, which contains all the information containing multi-molecule, all the constants and properties needed for us to do to complete these calculations. And I'm going to show you the one which I usually use for such calculations. Hold on a sec, please. Yeah, here it is. Yeah, you can see it. It's in Russian, but I hope that you can find similar references in your books and your manuals. Okay, we can see the word molecule as CO2, and it's written. It says that it's linear and symmetric, and we know that. It also gives us the internuclear distance in angstroms. It's 1.13. Okay, and we will need it maybe a bit later. Okay, and also it gives us the types of vibrations the molecule goes through. It has got 3 types: nu sub s, nu sub as, and delta sub as. Okay, and it also gives us the characteristic temperatures for each type of the vibrations, given in kelvins: 1944, 3448, and 968. As you can see, there are 3 degrees of freedom in terms of vibration. But not to make a mistake in our calculations, we also should pay a very close attention to the degeneracy, yeah, of each type of the vibrations. For example, for the vibration nu type S, we have no vibration. We have no degeneracy. For that reason, its coefficient is equal to 1. The same is about the second type of the vibration, nu sub as. However, we can see that we got the degree of degeneracy, which is equal to 2 for the third type of the vibration, delta sub as. For that reason, we will have to double our calculations related to the third type of the vibration. Okay, I strongly recommend that when you are uh, trying to complete such calculations, copy down all this information shortly into your copybook. Okay, and by saying this, I mean that you can see you can have it written down in your notebooks, and you make no mistake in this case. So very unlikely to make a mistake. Okay, let's return to our solution. Okay, here it is. So let me do the same what I just said. I'm going to copy down this information taken from the manual. So CO2 linear. Okay, the uh internuclear distance R sub A is equal to 1.13 angstroms. Okay, remember the angstrom means 10 raised to the minus 10th. Okay, and degeneracy 112. Okay, the types of abrasion: nu sub S, nu sub AS, and delta sub AS. Okay, then characteristic temperatures in Kelvin. Here in Russia, and I know that in England too, we have the symbol for the characteristic temperature as eta. It's a letter taken from the Greek ABC. This is how it's written again, eta. Okay, so for this vibration, it's as much as 1944. For the second, it is 3448, and for the last one, it is 968 kelvins. Okay, now in order to do the calculations, to complete the calculations, we should remember the formula. We need to calculate the vibration components for each type of the vibrations. I mean to say that we will have three components of the vibrational component of the internal energy. So let's do it for the first one. So U minus U sub 0 of vibration, okay, for nu delta S, nu sub S is equal to the gas constant times the characteristic temperature, let it be at the 1, divided by E, it's Euler number, right? E, exponent raised to at the 1 divided by T minus 1, okay? And now let's plug in the values to calculate this input. It's 8.314 times 1944. Okay, and divided by E raised to 1944 divided by 298, because this is the temperature. Here it is, minus 1, okay? And if you've got your calculators, you can see that the answer is equal to 23.85 joules per mole. Okay, we have just finished the calculations of the internal energy vibrational related to the first type of the vibration. Now we're going to do the same for the second type. We are writing that U minus U sub 0, okay, is vibration for nu sub AS is equal to the same formula, but the difference that now we're going to take not at the 1, but at the 2, this one, 3,448. So I'm not going to write down these formula because you can see it written here, but I will write down only the numerical values. 8.314 times 3448 divided by epsilon, I'm sorry, e raised to 3,448 divided by 928 minus 1. And that gives us 0.27 joules per mole. As you can see, its input is pretty low. However, we have to take this into consideration as well. Now we are doing the same for the third vibration. Okay, it's delta. Okay, so it's going to be much more. I guess so. Okay, minus 1, of course, and your calculator should show you the answer, which is close to this one, 325.76 joules per mole. And now we can, not can, we should sum all the three components related to the three types of the vibrations in this molecule together. Vibration. Okay. And the sum. So we sum of this, and this. And finally, we've got, oh, and again, you see, I nearly made a mistake. But we also should take into consideration the degeneracy, which is equal to 2 for this type of vibration in this molecule. For that reason, we write the following: it's 0.27 plus 23.85 for the next, but the third is doubled because of the degeneracy, which is equal to 2. It's 325.76. And finally, we've got the following. It's equal to 675.64 joules per mole. Okay. And now, on finishing the calculations related to the vibration input of the internal energy, we can start calculating the internal energy on the whole using this formula. This one. So the translation component of internal energy is equal to 3718.23 plus 2478.82. It's equal to the rotary component of the internal energy, and we have just calculated the vibration component, which is equal to 675.64, and totally the internal energy under these conditions, this temperature and this pressure, equal to 6,872.69 joules per mole. This is the answer for the first question, and we can tick it. Okay, now we can proceed to the second. It's very easy to do because we remember, so that's been the first one, right? Now we proceed to the second point of our calculations. It's very easy to do because we remember that H is equal to U plus R times T, right? We remember that from the course of thermodynamics, and we can apply this here. In other words, we can write that H minus H 0 is equal to U minus U 0 plus RT. We've just calculated this one. It's 6,872.69 plus 8.314 times temperature 298, So, and our assistants, which I call our calculators, should show us the answer, 9,351.51 joules per mole. Okay, this is the answer for the second point. So we are through with the second one. And now we are about to start the third, which is about the calculation of isobaric heat capacity. So I need more space. 1 second, please. Okay, okay. Yeah, it's going to be the third point of our calculations. Okay, let's do it. So we before we come up with the answer to this question, we need to do some um, other calculations. We should complete some other calculations, intermediate calculations, related to the calculations of isobaric heat capacity. Hold on a second, please. Yeah, it's my cat. It wanted to come out of the room. So, yeah, let's do it. Firstly, again, want to see that C sub V, V stands for constant volume. And this symbol means that we are dealing with pressure, which is equal to 1 atmosphere. Okay. So it's equal to CV translation plus CV rotary and plus CV um, vibrations. Okay. Now let's calculate each of these in turn. So C sub V translation is equal to I TR times R divided by 2. Remember that this the first is equal to 3, and that gives us that the isobaric heat capacity is equal to, I mean, its translation of input is equal to 12.471 joules per mole Kelvin. Then C sub V, but this time rotary, yeah? Oh, I'm sorry, not rotary, not yet. Oh, yeah, okay, let me rotary, yeah, rotary. Okay, it's I rotary times R halved, and we remember that this is equal to 2, and that gives us 8.314 joules per mole Kelvin. Okay, now the question is how to calculate the third component, vibrational. Firstly, we have seen we have already seen from the manual that we've got 3 types of vibration. For that reason, the vibrational isobaric heat capacity will also have 3 components of its own. We denote it as C sub E. Okay, we can write it's mu sub S for this type of vibration, yeah? It's equal to R times F1 divided by 2 by T squared times x okay, exponent raised to F1 divided by 2 by T and divided by e raised to f1 divided by t minus 1 squared. So let's plug in the values. We remember, I hope that you copy down f1. So f1 is 1944. 1944 divided by the temperature squared. So if you take your calculators, you will see it's saying that it's equal to 0.522 joules per mole Kelvin. As you see, it's not very great, but still considerable. Not to overlook it. So CE2, but not here. Look, it's delta A sub S. So the same formula, but the values are different. Instead of 1944, we plug in 3448, right? And if you use the same formula, but with alpha 2, you can see that this component is equal to 0.011 joules per mole Kelvin. Okay. So as you can see, it's not transferable, but still it gives its contribution to the total as a correct heat capacity in terms of vibration movement. And the last one, but not the least, as they say, is related to delta AS is equal to. So let me write down. So 8.314 times 968 divided by 298 squared e raised to this degree, okay, and divided by the squared difference. Oh, sorry. Oh, come on. And it's as much as 3.678 joules per mole Kelvin. In other words, we can write that C V operational is equal to C E 1 to 3 because 2 to the 3 C E sub E. Okay, and it gives. Oh, again, I was about to make this mistake. Never forget to take into consideration the degeneracy. I should multiply this component by 2 because we remember that for this type of vibration, the degeneracy is equal to 2, and that gives us 7.89 joules per mole Kelvin. Okay, and now we can write that C of V and 1 atmosphere is equal to, this is the formula, it's the translational component, 12.471 plus rotary component, which is equal to 8.314, and plus the vibrational component, which is equal to 7.890, and totally that gives us 28.675 joules per mole Kelvin. But they want us to calculate not as a correct heat capacity, but as a Berg. In order to do this, we should recollect Meyer's equation. Here it is. In other words, all we need to do is just to add the value of the gas constant to this number, 28.675 plus 8314, and we got 36.989 joules per mole Kelvin. Okay, this is the answer for the third item, for the first question. And if you look up the value of the isobar heat capacity for CO2 in a good manual reference book, you will see that it is nearly 37.11. As you see, what we got is very close to this one, and the relative how to say inaccuracy of calculations is roughly 0.33%, which is very, very good. Okay, we've just finished the calculations related to the isobaric heat capacity, and now we're proceeding to the fourth, where we are supposed to calculate the entropy. The scheme of the calculation is nearly the same. What I mean to say is this one, that the entropy of CO2 at temperature T and pressure 1 is equal to the entropy of the translation motion plus the entropy of rotary motion plus entropy of vibration, and each is going to be calculated separately. So first of all, let's start from the first component. Previously, I derived the formula for entropy translation calculation. It's equal to the gas constant R times 1.5 natural logarithm of the molar mass of this substance plus 2.5 natural logarithm of the temperature minus natural logarithm of the pressure plus 20.75. So let's complete the calculations. When we are using this formula, remember to use not grams per mole but kilograms per mole, which means that we write not 44 but 44 times 10 raised to the minus third plus 2.5 natural logarithm of 298 minus. And here we also have a trap. P, not 1 atmosphere, but in pascals, it's 101,325 pascals plus 20.75. So we use our calculators now, and the answer to this is 156. I'm sorry, 56.158 joules per mole Kelvin. Okay, so this is the first component. Now the rotary. In order to answer the questions, the question related to how much is or how large is the rotary component of the entropy, we need to remember the formula itself. The formula itself. S rotary is equal to R logarithm, natural logarithm of I, where I is the inertial moment of this molecule plus natural logarithm of temperature minus logarithm of sigma, where sigma is the symmetry coefficient of this molecule, plus 105.5. So we got two moments at this point to deal with, this one and this one. So as for the second one, it is very easy. The thing is that CO2 the symmetry is equal to 1. For that reason, the logarithm will be equal to 0. Okay, this is a good piece of news. And what about the moment of inertia? It's not that easy to calculate at this moment. In order to do this, we need to use the same reference in order to complete our calculations. Hold on a second, please. I'm looking for this in my reference, because there are a lot of different tables. Let's hold on a second, please. Just want to show you where I got all this from. Ah, oh my God. Hold on a second. Hold on a second, please. Yeah, I've got it. I've got it. Um, but the question is, yeah, uh, linear and symmetric. Mhm. Here it is. Um, this table, this table. So it's entitled as the main moments of inertia for different types of molecules. And here is what we need. This one. See, linear symmetric. Linear symmetric. Oh, and I was wrong saying that this symmetry coefficient is equal to 1. It's equal to 2, of course, because it's symmetric. And this is the formula given. It's twice the mass of the atom, the entropy of the molecule times squared internuclear distance r. Okay, we got what we need, and now we're getting back to our calculations. So let me rewrite the formula. So the inertial moment of CO2 is equal to 2 times the mass of the atom O, oxygen, times the squared internuclear distance between the atoms C and O, between the nucleus of carbon and oxygen. Okay, previously I got this information. It's equal to 1.13 angstroms. As for the mass of the atom, oxygen atom, it's very easy to know. All we need to do is just to divide the molar mass of the atom by the Avogadro constant, in kilograms of gas and to be divided by 6.2 times 10 raised to 20 to the 23rd. Okay, and that gives us 2.658 times 10 raised to the minus 26 kilograms. Okay, and then the moment of inertia of the molecule is equal to 2 times 2.658 times 10 raised to the minus 26th and 1.13 times 10 raised to the minus 10 squared. Okay, and that will give us 6.788 times 10 raised to the minus 46 kilograms times meter squared. And now we are ready to complete the rotary entropy component. Okay. Um, okay. Now temperature minus the liquid of 2 plus 105.5, and we got 54.043 joules per 9 7. Okay. This is the second, and now the vibration image. So I need extra space. Okay. So as for the vibrational components, again, there will be three vibrational components because there are three types of vibration, right? Just the same as we did with heat capacity. So as vibration for nu sub s is equal to, the formula is minus r times natural logarithm of 1 minus e raised to minus f1 divided by t, and then we add r times f1 divided by t and divided by e raised to f1 divided by t minus 1. Thanks God we've got good calculators. I hope that you do. And we'll remember that the first characteristic temperature is this one. And and that gives us the answer 0.092 joules per mole per Kelvin. Now, as vibration for mu a sub as, the same formula but with attitude. Attitude is equal to 3,448. and that gives us the answer 0.001. It's nearly negligible, but still we are supposed to write it and deal with it too. And the same formula for the third component, which is related to delta. Okay, equation. I will write down only the value which I've got. It's equal to 1.423 joules per mole Kelvin. Oh, I wrote down in Russian. Joule, of course, joule. Okay. Now remember to multiply this by 2 because again I want to emphasize because of the fact that the degeneracy for this vibration is equal to 2. So we can write that S vibration is equal to 0.092 plus 0.001 plus 2 times 1.423. And that gives us the answer 2.939 joules per mole per Kelvin. Okay, and now we can calculate the whole entropy of CO2 and at temperature T. So the translation component of the entropy is equal to 156.158. That for the rotary component is equal to 54.043, right? And the vibrational component is equal to 9.939, and that gives us the answer 213.14 joules per mole per Kelvin. This is the answer, and you see, if you compare it with the tabulated value, which you can find in a manual, you will see that it's very close to the one given there, because it's equal to 213.6. And the accuracy of our calculation in this case is less than 0.26%. Very, very accurate calculation. This is the value which provides us by thermodynamics, formula thermodynamics, and this one is what statistical thermodynamics gives us, which again proves that we got two approaches to deal with study of a thermodynamic system. It's either thermodynamical or molecular kinetic one, or in other words, statistical thermodynamic approach. Now, the rest are very easy. I mean, 0.5 and 0.6 are very easy to deal with. The calculation of reduced Helmholtz energy. The question is how to, what's the formula? But in order to derive the formula, let's remember the definition. Helmholtz energy is equal to U minus ST. Okay, so let's add E sub 0 to the both parts of this equation. I mean, not add, but subtract. And now let's divide the both parts of this equation by T. And this is actually the formula we need. And this one is what we call the reduced Helmholtz function. F minus U sub 0 over T is equal to, we have calculated this one, and it's equal to 6,872.69. We divided by the temperature, 298, and we have just calculated the value of the entropy, which is equal to 213.14, and that gives us minus 190.09 joules per mole per Kelvin. This is the answer. And now similarly, we can derive the formula for the reduced Gibbs energy. It's G minus H sub 0 over T. It's equal to H minus H0 over T minus S. Previously, above we calculated this value. It's equal to 9,351.51 divided by 298 minus 213.14, and that is equal to minus 181.77 joules per mole Kelvin. Again, I want to emphasize the fact that the value, I'm sorry, the measurement unit for these two functions is seen from the formula joules per mole divided by temperature. That means joules per mole per Kelvin. And this is the answer for the last question. This is the end of the solution. I hope that you have learned something interesting. If not, but at least you have had a chance to brush up on your computational skills related to physical chemistry, statistical thermodynamics. Thank you very much for your attention.